sample. Our sample, this is the example of the crystal cluster of our sample. And from this, we can also determine or calculate the position of all other elements and the occupancy of all elements in the structure. From this part of X-ray diffraction, we can also calculate the crystallite side and average lattice strain with Williamson Hall with using this formula. Here we have obtained from X-ray powder diffraction, the crystalline size is about 67 or 66 nanometer for this kind of samples. Now I will talk about magnetic measurements, which is very important in our study. Here we have magnetization as a function of temperature of this kind of sample with an applied magnetic field about 0.05 Tesla. We can see that we have a paramagnetic to a ferromagnetic state transition with decreasing the temperature and with increasing the content of the sample. The Curie temperature was determined by for this kind of sample, and we can see that when we substitute manganese by cobalt, the Curie temperature decreases from 256 K to 175 K for this kind of sample. What is the magnetocaloric effect? So, which call it MCE. We have we use right now called production using a classical technique for compression and relaxation of gas. So they are greenhouse gases that contribute to global warming. These gases are so identified as the main causes of the depletion of the ozone layer. From this, we have some solution, and the solution are the refrigeration without the refrigerant gas and with the low energy consumption.
Sir, I request you to please bind within 5 minutes so that we are running out of time, sir. Sir, it's a request to you.
Okay.
Okay.
So the solution is the magnetic refrigeration is one of the way that can solve this problem. What is the magnetocaloric effect? Some materials heat under applied magnetic field. This phenomena is called the magnetocaloric effect. Materials providing this effect are called magnetocaloric materials. By using the magnetocaloric effect, a magnetic cooling cycle close to room temperature is possible. Now, how was the effect discovered? This effect was first postulated theoretically in the work of Langevin in 1905. He predicted that the temperature of paramagnetic materials should have, depending on the magnetic field. Magnetocaloric was first observed in experiment by Weiss and Picard in 1917, where they could measure a temperature change of nickel upon application of magnetic field. What is the magnetocaloric effect? It's manifested by the changing of thermodynamic state of magnetic materials in an external magnetic field, depending on the condition which is in which the magnetic field is applied, either the change of thermal entropy or adiabatic temperature are commonly used to numerical parameter characterizing the magnitude of magnetocaloric effect. How does the magnetocaloric effect work? With the increase in applied magnetic field causes the magnetic moment line to parallel to magnetic field, which is decreasing the magnetic entropy due to the adiabatic condition within the system. The total energy of the system remains constant and the material is heated. So after that, we can suppress the magnetic field. Once we suppress the magnetic field, we have another state of entropy. What are the magnetocaloric materials? Metals with the magnetocaloric effect. These metals include pure elements such as gadolinium or alloys. This is a photo of gadolinium, natural gadolinium. So this kind of natural gadolinium is the reference of material at room temperature, and we have a Curie temperature above the room temperature. We have also variation of magnetic entropy, which is about 10 joule per kilogram per Kelvin, which have an RCP and higher RCP. The problem is that gadolinium is very cost, as well as it is easy to oxidize, which decreases this performance. So the solution, among the solution, is the manganese, which is cheaper materials that are easy to synthesize and have magnetocaloric effect in every temperature. So here's the principle of magnetocaloric effect. When we apply a magnetic field, so we have a heating, so we have magnetization. Then when we suppress the magnetic field, we have a cooling. And this is the two part of physical quantity alone to calculate the effect, magnetocaloric effect. This part is from the variation of entropy, and this part is the variation of temperature. This is the formula with magnetic measurement, and this is the formula with using a specific heat measurement, which call it the direct information of this kind of magnetocaloric. So here we have some variation of magnetization as a function of applied magnetic field at different temperature, and for some series of samples, and this part of magnetization versus applied magnetic field and at different temperature should be done between paramagnetic state and the ferromagnetic state of this of our samples. So here we have also performed the variation of specific heat of as a function of temperature applied versus applied magnetic field, and we can see that from this we can deduce the Curie temperature of our sample, and from this part also we can have the variation of magnetic entropy as a function of applied magnetic field and temperature for all the samples. So there is also, which is very important for this kind of samples, which called criteria of performance, which is used by this formula, is the variation of entropy magnetization of the maximum and the distance between the half of the peak and the half peak of temperature, and the good performance criteria of performance RCP give us a good idea about the using of our samples. So here we have some results also about our main results of magnetic properties, which are from two kinds of results, variation of magnetic entropy and the variation of temperature, adiabatic temperature. And we have also the RCP for this kind of sample with different formula. This is the formula for using magnetic entropy, and this is the formula using adiabatic temperature. Here also the some results about the RCP and for some reference gadolinium or the other, and all of the other are for our samples, and we can see that we have sometimes some RCP which is very near close to close to Curie temperature, and so it's different from those gadolinium lower, so we can improve this RCP using other method. Here is an example of RCP of other samples also. This is deduced from our work. Here also the variation of RCP as well as the variation of magnetic entropy, and we can see that from this kind of sample we have lower entropy, magnetic entropy, but we have a good RCP. But for the other, this one, we have the difference. We have lower RCP and we have a good value of variation of magnetic entropy. Let's start now to another different of Manitou caloric effect, not in oxides, but in compound with formula gadolinium 2 iron 70, which are very interesting for paramagnetic, for magnetization, which are non-oxygen. Here we have powder X-ray diffraction of refinement of our sample, and we can deduce that there is no impurity in our sample. Here also we have the magnetization versus applied magnetic field versus temperature, and applied magnetic field, which is about 0.05 Tesla. And we can see that the Curie temperature is higher than the room temperature, which is about 400 Kelvin. Here we have the structure of this kind of sample, and this is it's not so easy to calculate or determine the structure using the foolproof software, and we have the possibility also to get this structure. Here we have also performant magnetization versus applied magnetic field at different temperature for this kind of sample. And we have also using this formula, using this result, and using the formula between magnetic entropy and magnetization, we can introduce also and calculate also the variation of entropy in this kind of sample. Here we have also a new approach that use Monte Carlo simulation of to determine the thermal magnetization and at different magnetic field, and to determine also the Curie temperature of our sample. And we have also, using the Monte Carlo simulation, we can also calculate the variation of entropy of our sample, and we can see that we have also the same variation of magnetization of applied magnetic field for this kind of sample, as well as the magnetic entropy. What is now the future? Future now is in this kind of oxide, it's in Manitou caloric effect. So, as I said, from this kind of sample, we have variation of temperature of half temperature of the peak of magnetic entropy. So the future, if so, is how to increase the RCP using this formula and using the variation of temperature. So when we prepare samples with different value of X and different value of concentration of substitution, so we have different entropy, variation of entropy. So we have, yes, I will conclude.
Dear Yellow, this is Rathiram. Please try to complete.
Using this, that we can increase delta T if, on the layers of in composite, so we can also increase the RCP then using a series of samples at different value of X. So we conclude now. For the manganese oxide, we have some advantages. We have a low saturation, nanoparticle also are observed, and no corrosion and easy to synthesize. The inconvenient, it's a low magnetic density. For metallic alloys, we have advantages: high magnetic density, low magnetic saturation, relatively nanoparticle, and we have some corrosion and mixing, and I didn't talk about this in this lecture. And both manganese and the metallic alloys are potential magnetocaloric material candidate for cooling system based on magnetic refrigeration. I hope to thank also our collaborator Hilil Kibir from France, Sami Mahmoud from Jordan, Sana Zweri from Tunisia, Faris Ben Jamah from Tunisia, Abdullah Turki from Tunisia, and thank you very much.
Thank you, Dr. Muhammad Ilus, sir. Now it's time for question hours. If anybody have a question, they can ask, please.
That dear Yellow, this is Rathiram. Is it audible? Are you hearing me?
Sorry?
I have one question regarding just like that is magnetite, and then you have written that dimixon. So, what is that dimixon?
What? I don't understand. Sorry?
In your last slide, you have written that dimexon. So, what is the dimexon?
Is mixing.
Acha, it is mixing. Yeah. That's fine. Yes. Okay. Thank you so much. Really, it was a wonderful talk.
Thank you very much.
Yeah.
Thank you. Now, I invite Dr. Rathiram Chaudhary, convener of the conference and head of department chemistry, to introduce today's eminent speaker, Dr. Martin F. Desmond. He is a professor at Tiloro University, Argentina. Over to you, Rathiram sir.
Thank you, Dr. Alok Rai, giving me opportunity to read out the biography of Dr. Deshmani. Martin Deshmani was born in Buenos Aires, Argentina. He graduated from pharmacy and biochemistry and received his PhD degree from the University of Buenos Aires. Currently, he is a concept researcher and professor in the Faculty of Pharmacy and Biochemistry at the University of Buenos Aires. He was a recipient of awards and distinctions, including the participation in the 2016 Emerging Investigator themed issue of the journal of Material Chemistry B. The award innovator in the category Applied Research received in 2 years, 2016 and 17, from the Ministry of the Science and Technology and Productive Innovation, MNCYT. The distinguished of Dr. Joseph A. Balserio of 15th edition received in the Argentine Senate, which is the upper house of the Argentina National Congress, International Association of Advanced Material, that is IIM, Medal of the year 2016 for notable and outstanding research in the field, Stockholm, Sweden. He is also a member of IIM Fellow. He is also Fellow of IIM Fellow. He reviewed the academic excellence from the UBA. He co-authors of 103 journals publication and 17 book chapters and 4 patents. Apart from this, I would like to tell you that he edited 4 to 5 thematic issues, as well published more than 16 review articles. So such dynamic and energetic personality with us. So I request my friend Martin Deshumani to deliver talk on biotechnology, the forward path. And I as well request to my the Deshumani, please try to complete in 20 minutes. So
okay.
all to you. Yes, all to you, Martin.
Thank you very much, Ratjam. I am delighted
My pleasure.
to be. Can you hear me?
Yeah. Is it audible?
Okay. So I am delighted to be early this morning here in Argentina. It's about 5 a.m.
Yeah.
So it's a real honor to give this lecture for you. I would like to thank to the organizers and especially to Professor Ratiram Chowdhury for the invitation to share our work with you. So I hope you can find it interesting. I will try to do it in 20 minutes. Just tell me if I must go faster. I will talk, let me see. This is the outline of my talk. I will talk about nanoparticles, especially designed for biomedical applications. I will give few examples about drug delivery, an example about nanovenoms, nanobiosensors, clean synthesis of nanomaterials, and some concluding remarks. What we know, what we use from nanotechnology is that we can prepare nanoparticles with different size, just adjusting the conditions for the synthesis of these nanoparticles. We can prepare nanoparticles of the decided size. We can go from monomers, dimers, trimers, and obtain different nanoparticles. In this talk, I will focus on silica nanoparticles. The interesting thing of these nanoparticles is that we can make different surface modifications of the nanoparticles, and we can have nanoparticles with silanol groups, nanoparticles with anamine functional groups on the surface. This is very interesting because we can have nanoparticles with different behavior. These particles possess a negative zeta potential, and this one possesses a positive zeta potential at neutral pH. And we can make other kind of modification, for example, introduce thiol groups or sulfonate groups. So the chemistry at the nanoscale is well known, and everybody can take advantage of these nanoparticles. Especially in the biomedical field, we can design nanoparticles, especially with the properties required to transport different antibiotics. For example, in this case, we prepare nanoparticles with sulfonate groups or silanol groups that are the more advantageous for the delivery of this antibiotic, it is gentamicin. And we can prepare nanoparticles with thiol groups on the surface that are more appropriate for the delivery of this second antibiotic, this is rifamycin. This is mainly due to the surface interactions established within the sulfonate groups of the nanoparticles and the molecules of the antibiotics. In a step forward, we can prepare nanoparticles with the ability to transport different types of therapeutic molecules. For example, we can prepare core shell particles in which we have a core of the nanoparticles. We can make the first grafting with the ability to interact with the first drug, in this case it's the first antibiotic. Then we can make a shell of the material, in this case silica material, and make a second modification of the surface of these core shell nanoparticles. And in this case, incorporate the second drug, in this case it is the second antibiotic. So we can have one particle, in this case, with the ability to transport two different antibiotics. The interesting thing of these core shell particles is that their behavior is strongly depending on the properties of the sulfonate of the surface group present on the nanoparticles. For example, those particles with core shell, that have a thiol group in the core and a sulfonate group in the surface, possess a similar behavior to those nanoparticles with only a sulfonate group on the surface. The same here, those particles with only a sulfonate group in the core and a thiol group on the surface possess the same behavior in terms of zeta potential to those of only a thiol group on the surface. Here we have some transmission electron microscopy and scanning electron microscopy of the nanoparticles. Here we see that when we have some antibiotics present in the core of the nanoparticles, when we make the shell of the particles, there is some rugosity due to the presence of the organic molecules present in the core. This is very, very interesting because we can have particles especially designed to deliver both antibiotics. As I mentioned, our strategy was to put gentamicin in the core of the particles, and then we make the shell and put rifamycin in the shell, so we can deliver two types of antibiotics. We follow the release of both antibiotics, and we confirm that both can be released from these core shell nanoparticles. And what is interesting is to evaluate their antimicrobial activity. What we observe is that the core shell particles alone don't have antimicrobial activity. We evaluate first with this Pseudomonas aeruginosa bacteria, that is a gram-negative bacteria. Those core shell particles with only rifamycin are not effective against this bacteria. This is mainly due because this rifamycin is not effective to kill this bacteria. The core shell particles with only gentamicins are highly active and effective against this bacteria, and the activity of the core shell with both antibiotics is similar to the particles with only gentamicin, because as I told you, rifamycin is not effective against this bacteria. Then we evaluate our system in a gram-positive bacteria like Staphylococcus aureus. What we observe again is that the nanoparticles without antibiotics are not effective. Those with rifamycins are effective in this case. Those with gentamicin are also effective, but the core shell with both antibiotics possess a real and significantly improved antimicrobial effect. We can use these silica nanoparticles for different applications, especially in the biomedical field. We use this to prepare different material for tissue engineering applications, because we can use these particles to prepare different biomaterials, and these materials can have antimicrobial activity, thus avoiding the infection of the wounds. So in this field, we prepare different works in recent years about the combination of these nanoparticles with collagen hydrogels to prepare nanocomposite materials and their ability to release these antibiotics. But in recent years, we also evaluate what happened with these nanoparticles if they enter in contact with cells, because if we use them in biomaterials, they can enter in contact with different tissues. So we evaluate the effect of nanoparticles of different sites on monocytes. These are specialized cells that work in the immune systems. For example, we use different flow cytometry assays. And to summarize our results, we can say that small nanoparticles, they don't have a strong effect on the proliferation of the cells. This means that the cell can proliferate in a normal behavior. There are not production of cytokines responsible of the activation of the cells. This could be indicative of an immune activation of the cells. This don't happen in the presence of small size silica nanoparticles. That these very small silica nanoparticles can be used for the delivery of different therapeutic molecules. On the other hand, nanoparticles of 200 nanometers or more produce a strong activation of these cells. There is a strong production of different cytokines. These are involved in the activation of the cells and the immune response. There are some cellular markers activation. The proliferation of the cell was significantly lower. Thus, these particles possess a pro-inflammatory effect and can be used, for example, as adjuvant in the production of vaccines. We also evaluate the effect of the surface modification of the nanoparticles. We compare, for example, nanoparticles of the same size with silanol groups on the surface. These particles possess a negative zeta potential. And we compare with the effect of silica nanoparticles with an amine functional group on the surface. These particles possess a positive zeta potential. And we evaluate their effect on cells present in the immune system, for example, monocytes. With negative zeta potential particles, those with silanol groups on the surface, you observe that the proliferation of the cell was lower, as I mentioned in the example before. There is a strong activation of these cells with an increase in the production of different interleukins, interleukin 8, 12, nitrates. The presence of different cellular markers is also increased, and the cell membrane is damaged. While when we use amine grafted silica nanoparticles, these particles with a positive zeta potential, the proliferation of the cell was not affected, and the activation of the cell was significantly lower. We can use this effect to deliver different therapeutic molecules, especially because we know which surface modification is better. And some of these effects that we observed, it was reported that the mechanism for the cell damage is the production of reactive oxygen species. Thus, the incorporation of antioxidant molecules in these nanoparticles could be highly beneficial for the therapeutic application. So we evaluate the delivery of N-acetylcysteine. This is an antioxidant molecule. This is very difficult to apply because it cannot enter the cells very easy. So in this case, we prepare hollow silica nanoparticles like this one, because these particles can transport a big amount of these therapeutic molecules. What we observe is that in these nanoparticles with the N-acetylcysteine produce an effect on the proliferation of the cells, and this effect is dose dependent. So if we increase the amount of silica nanoparticles, we observe a diminution in the viability of the cells. But to avoid this effect, what we make is to coat the nanoparticles with proteins. In this case, we evaluate what happens if we absorb albumin in the surface of the nanoparticles. And what we observed that when the nanoparticles have a shell of this protein, the viability of the cell is not affected. Moreover, the production of reactive oxygen species was significantly higher when we expose the cells to the silica nanoparticles. This effect is dose dependent. This means that if we use more nanoparticles, there is more production of these reactive oxygen species, but the production of these rows is significantly lower when we use nanoparticles with the albumin absorbed in the surface. This means that we can use these nanoparticles to transport proteins. This is very important from a biotechnology point of view. That's why I use this bionanotechnology in the title of this lecture. And for example, I will go to the example of the application of these silica nanoparticles to prepare nanovenoms. In this case, we absorb different proteins present in the venom of this very nice species. This has a very toxic venom. We prepare these nanoparticles, these silica nanoparticles with proteins present in the venom of this venom. We obtain the nanovenoms and we make the characterization, some physicochemical characterization and biological characterization. What we observe in the nanoparticles is...
Martin, excuse me.
Yes.
You have 5 minutes left.
Okay. What we observe is that these nanoparticles has a core of the absorbed proteins on the surface. We make the characterization by infrared spectroscopy. We also observe the characterization by SDS and Western blot analysis, and we confirm the presence of the proteins of the venom present on the surface of the nanoparticles. And we evaluate the activity because some of these proteins present on the venoms are enzymes, and we have observed that these enzymes absorbed on the nanoparticles are really active, so the conformation of the protein is maintained. So this is very important for the preparation of these nanovenoms that could be used, for example, for the production of antisera in the injection of different animals, for example. Moreover, this venom possesses some anti-proliferative effect on cells, and what we observe that when we use nanoparticles with these protein absorbers, the effect is similar to those of the venom alone. So these proteins absorbed on the silica particles are fully active. And the next example that I would like to mention in this field with proteins and nanoparticles is the design of a biosensor assay to improve the detection of different enterotoxins or superantigens. In this case, we use the sulfate plasmon resonance. In this case, we have the light incidence on the surface. We have some antibodies that can absorb it on the surface of this system. And when the antigen interacts with this antibody, the reflected light changes the angle, and this is what we use for the detection. So we observe when the antigen is present, a change in this angle, and this is how we observe the signals. Since it is a flow channel, when the antigens arrive, the signal rises. And when we remove the antigen, the signal goes down again. This is how this works. And what we make is that, or what we observe is that instead of using only antibodies, we employ silica nanoparticles with these antibodies. The detection of the antigens, the signal obtained is significantly higher, so we can amplify the signal of this biosensor by employing nanoparticles with absorbed antibodies instead of using antibodies alone. So in this way, we can amplify the signal of these biosensors. Well, the nanomaterials application is growing very fast, but we observed in recent years that it's growing very fast also is the nanotoxicological effect of these nanomaterials. So we must have in mind the effect of these nanomaterials, especially because we can get exposed to nanomaterials during different steps. For example, we can get in contact with nanomaterials during their production, during their use, or during their disposal. They can have an impact on the environment and also in humans and in the biota. And this depends on different properties of the nanoparticles, and also environmental factors are important on the effect that these nanoparticles can produce. In this sense, the effect, nanotoxic effect of silica nanoparticles was reported in different species during the last years. That's what appears as a very interesting feature for the next years is the production or the green synthesis production of nanostructures or nanomaterials. In these fields, in recent years, we produce different nanomaterials. We have some publications in these fields, also with some of you present here today, like Professor Ratiram Chowdhury and Professor Raftre Kotania also. We can prepare very nice nanostructures and very useful for catalysis, drug delivery, antimicrobial effects, and other effects. Also, with Professor Chowdhury, we prepared 2 different special issues for journal Current Pharmaceutical Biotechnology with a good number of reviews about this field. So this is a very interesting field for coming years. And just to be on time, I will mention my team here in Argentina with some young researchers, postdocs, students. Here is my team, some collaborations related to the work that I presented today, also with some of you present in this conference. And thank you very much for your attention. Here is my contact if you want to get in contact. Thank you very much for this award that I received yesterday. I feel really honored of this award. I would like to thank you all the organization for this award, but I also want to thank especially Professor Chowdhury, my friend. We met with Ratiram in 2018 in a congress in Sweden. That was the beginning. I read this sentence in the award that I received, in the letter of award that I received, and it's very true. I will use few seconds more to talk about this, because the beginning was in Sweden. This keeping together in progress, and it's very true, because Ratiram was very active to make us work together, and it was a very good progress for us. And since then, we start to work together, and this is success because we produce different works together, different publications, and also the networks grow very fast during the years with collaboration with other members of this group that was created by Professor Chowdhury. So thank you very much. It was really, really a good work. So that's the end. So if some of you want to get in contact, you can send me an email, or you can find me also in the social networks to find some updates about our work. Thank you very much.
Thank you, Dr. Martin, for such a wonderful lecture. Now the session is open for question. If anybody wants Please ask.
Excuse me, sir. I have one question related to 3D3L1 cell lines. Sir, these cell lines require to convert pre-adipocyte into mature adipocyte by means of transcription factors. So, sir, would you please enlighten us that how nanoparticles can modulate the gene expression via transcription factors? Why? Because I'm asking this because I came to know that you are also biochemist. Hence, sir, asking you, sir, how these nanoparticles can modulate the transcription factors. Thank you, sir.
Good lecture.
Well, these nanoparticles can have different effects on the nanoparticles. One is that they can produce some oxidative stress on the nanoparticles, and this can lead the cells to respond to this effect, try to contrarrest this effect, and they increase the production of reactive oxygen species. And this can have an effect on the transcription of different proteins on the cells. But also these nanoparticles can be used to deliver different genes to the cells, and this can be used to use the production of other proteins, for example. I don't know if this is your question.
Thank you so much.
Thank you, Dr. Martin.
Thank you very much.
Thank you, sir. Now
Martin,
I
it was Martin, it was a nice lecture. You can continue.
Now I invite Dr. Dhanraj Masram sir, Associate Professor, Delhi University, for conclusion of this session. Over to you, Dhanraj sir.
Greetings to everybody. Myself Dhanraj, and overall to see this session. This session is very nice. It's dealing with the whole biological interaction.
Sir, your device sound is not, I think, audible to us. Please.
Unmute it.
Am I audible now?
Yeah, it's good.
Okay. So warm greetings to everybody. I'm happy to participate this very beautiful and knowledgeable and knowledgeous round of our technical sessions, where we have heard three eminent scientists, Professor Mohammad Kurus, Mohammad Elias, and Professor Martin, and all of them have given us very knowledge about the biology and biological reactions and its usefulness to the society overall. The first lecture given by Professor Kudus was emphasizing on the extremozymes and extremophiles and its sustainable sources of bio-based economy, which is very useful for the biomedical applications as well as the biological importance in the society. Second lecture was delivered very beautifully and explained very nicely by Professor Elias, who has given the knowledge about magnetism and magnetocaloric values and its effects of perovskite in the various application of the various facets of the science. And the last but not the least, it was enlightened by Professor Martin, and he have given us very nice, beautiful and simple language where we came to know about the biotechnology, which is useful for our drug delivery, cell structure, and its importance for the cell line and overall biomedical application of that nanoparticles and its nanotechnological effects for the researchers who have present in these sessions. And I'm really thankful for all these three dignitaries who have enlightened us with their knowledge. I'm also thankful to our team, Professor Dr. Alok, Dr. Dongre, Dr. Mondal, Dr. Ratiram Chaudhary, Dr. Subhash, Dr. Rahul, Dr. Kadam ma'am. And above all, I'm also thankful to our college who have supported us for this conference and encouraging us, providing full support and freedom to conduct this conference. And especially I'm thankful to Ambedkar College, Urval College, and Priyadarshini College. And above all, I will be failing to make a vote of thanks to RTM Nagpur University Nagpur for providing platform to all the researchers and its teachers and the stakeholders present over this conference and supported by its hard work and all source. And I'm also thankful to the organizing committee for giving me this chance also. So I'm grateful to all of you for joining this session. And with this, I may say that this session, this wonderful session is come to the conclusion. And this way we have concluded our conference also in the form of technical sessions. Now, validatory function will be commenced after that. So I may be inviting you, and I'm honored to invite you for this function of validatory. Thank you very much. Thank you very much, sir.
Thank you, Dr. Dhanraj Meshram, sir. So there will be a 15 minutes break. After that, we will start the validity function. Please be noted. Thank you very much.
Thank you one and all who were present in this technical session 3 and 4. Now we will join